So if now we'll extend this notation to the cases where x is not a scalar. So if x is a vector of size 2 by 1, then phi of x of this vector is just simply applying these basis functions to x1 and put them in the first row. So this is phi1 x1, phi2 x1, all the way to phi m x1, and the second row is just basis function evaluated at x2. So the size of this matrix is the size of this vector, because the number of rows is the number of points we are evaluating this. So here this is 2 by m. And you can take this x to be all the training data. And so it's just a straightforward extension of this. So now you have the basis function evaluated, like I said, at each. This is the first row is the basis function evaluated at x1, the same way as we had it for a vector of size 2 by 1. And this is phi1 at x2, phi2 at x2. Then the last row is all the basis functions evaluated at xn. So the size of this, we have n rows, we have n basis functions. So now this is a matrix. Okay, so this was the case where x was a scalar. Here is the case where x is a vector. All right, so now using this notation, if you want to evaluate f at all these points. So let's say x is this vector of training points again. I was using the same x here. What this really means is that f evaluated, any function that we have the same way, is evaluated for x1. Remember, even if we want to evaluate f mol at a particular x, we still need the entire vector of theta. Because if you plug in x, a particular x, let's say x1 here, you still need multiply e of x1 times theta 1 and e phi2 of x1 theta 2 and so on and so forth. So that's why I put the entire vector here, but now x1 is a scalar. It's just one component of this vector. And the second component is this, and now this is a vector of n by 1. And so it's actually, because this is now a vector, I'm going to put an arrowhead on top of f as well. So the reason I didn't put an arrowhead for phi when we had x1 only, because that was the special case of a matrix. For phi in general, the matrix of all basis function evaluated at all points is in general a matrix. But f at most is a vector. F doesn't become a matrix in this notation. So now let's see if we want to write the expansion, if we want to evaluate f at all points for all the basis function, what that looks like in the matrix vector formulation. It's still really the same form. So f of x bar, this is f evaluated at all these x. So the size of this vector f is always the size of the vector x. That is just simply equal to p evaluated at all x and theta. So let's look at this from the linear algebra point of view. So this is a vector of size n by 1 because that's the size of x. This is a matrix of size n by m, as we've shown here. And theta is n by 1. So if you multiply this n by m times this vector n by 1, you get n by 1, which is this vector. If you look at this row, every row multiplied by that vector is basically the summation over all basis function. Every multiplication here, so if you look at this, this is theta 1, theta 2, theta m. If you just plug in this basis function here, phi1, x1, phi2, x1, pm, x1, just evaluate this. The first row here is really the inner product of this first row and this column, which is the summation of phi1, theta 1, plus phi2, theta 2, all the way plus phi m, theta m. All evaluated at x1. And that's what you want as the first row. And if you go to the second row, you just switch x1 to x2 and exactly give you that expression. So this really compact expression covers all cases of linear regression. And you will see actually this can help us in terms of formulating the loss function and taking the derivative, ultimately solving that linear system.